Okay, so we finished our discussion of radiation, which is one way of transferring energy from place to place in the atmosphere. So now we're going to talk about a second way of transferring energy, which is good old-fashioned heat transfer. Now, as suggested by the title to this slide, there's actually 3 different ways you can transfer heat in the atmosphere. We're going to talk about each of these in some detail and explain them on the following slides, but for the moment, I just want to go through and list them one by one. So our 3 ways of transferring heat in the atmosphere are going to be conduction, convection, and latent heat. Latent heat. Conduction, convection, and latent heat. So let's go through and talk about each of these one by one. Now, the first way of transferring heat in the atmosphere has to do with the motion of the molecules in the substance. If you remember back to when we talked about thermal energy and temperature, what thermal energy really is just the molecules bouncing around faster or slower. If there's something that's warmer, it just means the molecules are bouncing around faster. Now, if you've got part of an object that's warm, that means in that part of the object, the molecules are going to be bouncing around fast. And what can happen is that those molecules end up bouncing and colliding into the molecules next to them, which makes them bounce around a little faster. And they collide with the molecules next to them, which makes them bounce around a little faster, and so forth and so on. You end up transferring thermal energy through the object just by the molecules bouncing around and colliding with the molecules next to them. So the example that's given down here is what happens if you put a metal rod into a candle. So initially, the part of the rod that's in the candle flame is going to warm up, which means the molecules are going to start bouncing around really fast. They'll, of course, collide with the molecules next to them and make them bounce around fast, and they collide with the molecules next to them, and so forth and so on. And this thermal energy then ends up getting transferred along the rod until eventually it reaches your fingers, and it's going to end up burning your fingers. So this process, of course, has a name. So when heat is sort of diffused in this way through an object, passing from molecule to molecule as they bounce around faster and collide with each other, this process is referred to as conduction. This is conduction of heat, molecule to molecule. Now, as you might expect, some substances are better at doing this than other substances, and as it turns out, air is actually pretty bad at transferring heat in this way. Air is a pretty poor conductor of heat. Another way to say the same thing is that air is actually a pretty good insulator because it doesn't want to transfer the heat. This is why if you look closely at your windows, if you guys have a somewhat newish house, you'll see that your windows are not actually just one pane of glass. They're actually 2 panes of glass, and in between they've got a layer of gas. It's usually not actually air. It used to be air, but nowadays it's usually argon or krypton, xenon, things like that. But it's the same idea. That layer of gas sitting between the panes of glass doesn't like to transfer heat through conduction. It's a good insulator of heat. And so as a result, it makes the window much more energy efficient to have that layer of gas. In fact, a lot of the good windows, the really good windows, will have 3 panes of glass, and in between there's 2 layers of gas, which is even better at insulating. Now, because air is pretty poor at transferring heat in this way, it actually doesn't manage to transfer it very far. So let's suppose we've got a situation where we've got the ground warming up over the course of the day by absorbing radiation from the sun. As the ground warms up, the air next to it will warm up too by direct contact. And so that thermal energy will start to diffuse its way upwards through the atmosphere with molecules colliding with the other molecules next to them and transferring the energy upwards. But because the air is so bad at doing that, it actually is only a very thin layer that ends up being warmed that way. It's surprisingly thin. It ends up being on the order of centimeters that manages to get warmed directly by contact with the ground. Now, another way we can transfer heat, if we have something like a liquid or a gas where we can actually sort of rearrange it, move parts of it to other places, then another way we can transfer heat is by taking a whole air mass and moving it to another place. So if we have an air mass that's warm and we move it somewhere, then that's a transfer of thermal energy, right? We took that warm air mass and moved it somewhere else. The example that's given down here is a situation where we've got sort of a hot spot on the ground. And this is actually the same process, just at 3 different times. You can see the times listed down here on the bottom. So it's sort of an evolution of the same process. And initially what happens is you've got this sort of hotter spot at the ground. Maybe it's a big parking lot or something that's getting really warm. And so the air next to it will start to warm up through conduction. And little by little, that'll start to bubble its way up. That warm air is going to be less dense because it's warm. Being less dense, it's going to want to rise. And so you end up getting bubbles of warm air that work their way up, and they'll coalesce into bigger bubbles. And eventually you'll get this sort of bubble of hot air sitting over, relatively hot air sitting over your parking lot. That hot air will start to rise more and more, and eventually it'll actually detach and sort of work its way up through the atmosphere. This is one type of a thermal, with the warm air rising. Now, as a result, we've actually transferred energy upwards, right? We've taken this warm air mass and moved it upwards, and so there's an upwards transfer of thermal energy. But this didn't happen by the molecules colliding around with each other. The transfer of energy happened by taking this whole air mass that was warm and moving it upwards. So this process also, of course, has a name. So when heat is moved around from place to place due to warm and cold air masses moving around, so if you're transferring heat from place to place just by moving around the warm and cold air masses, this guy is called convection. That's called convection. Convection is taking a warm air mass and moving it somewhere else and thereby transferring thermal energy. A couple of notes about this. The first is some terminology. We use slightly non-standard terminology maybe in the atmospheric sciences. It's standard for us, but maybe it's a little bit different from what's used in other disciplines in that we separate out this transfer of warm air masses when it happens in the vertical and when it happens horizontally. Whenever we have a warm air mass moving in the vertical and transferring energy that way, so if it transfer of energy in the vertical, that we typically refer to as convection. So that was the same as example on the previous slide. We had that warm bubble working its way up through the atmosphere. We would typically refer to that as convection. On the other hand, if we have a warm air mass that we move somewhere horizontally, for example, suppose we've got warm air to the south and something happens to cause that warm air to move northward, that's a transfer of thermal energy horizontally. And when that happens, instead of calling it convection, we usually use the terminology advection. Advection. So the motion of warmer air masses vertically is called convection, and the motion of warmer air masses horizontally is called advection. The reason we do that is because it turns out that the kinds of processes that cause warm air masses to rise are very different from the kinds of processes that cause them to move around in the horizontal. So we kind of separate them out with different names in this way by calling them convection for the vertical and advection for the horizontal. Now, the second thing to point out about this is that when compared to conduction, which was very inefficient in the atmosphere, convection is a much more effective way of transferring the heat. So in fact, it's going to end up being the main way that we transfer heat from place to place directly is going to end up being through convection as opposed to conduction. Okay, and then the third way of transferring heat in the atmosphere is maybe a little bit more subtle, and it has to do with transformations between the phases of water. The basic idea is that water can exist in any of its three phases in the atmosphere. You can have water vapor, of course. You can have the liquid phase, which would be cloud droplets and rain droplets. And then you can have the solid phase as well, which would be ice, cloud ice, snow, hail, things like that are all going to be the solid phase. And so depending on the conditions, the water can go back and forth between these phases. And anytime that water goes from one phase to another, it turns out that there is an exchange of energy in the form of heat with the environment. So specifically, certain kinds of transformations of phase are going to release heat to the environment, and other kinds of transformation of phase are going to extract heat from the environment. So of course, this has a name also. So transformations in between the phases of water vapor. Transformation between the phases of water vapor, which are referred to as phase changes. So phase changes of water vapor. Anytime we have a phase change, this is accompanied by either the release or absorption of heat from the environment. So we're either releasing heat to the environment or the absorption of heat from the environment. And this is referred to as latent heat or latent heating when it's actually sort of in action. So the exchange of energy with the environment due to phase changes is called latent heating. And of course, the reason this is relevant for our purposes is that if we have a process, a phase change that releases heat to the surroundings, that's going to end up warming the surrounding air. By contrast, if we extract heat from the surroundings, we absorb heat from the surroundings, that's going to end up cooling the surrounding air by taking heat away. Now, it's probably worth going through and making a little... Oh, actually, first, before we do that, it's probably worth going through a little schematic to sort of illustrate, sort of give sort of an intuitive idea of how this works. So let's suppose that we've got liquid water. So we've got a little cloud droplet, and we've got our molecules bouncing around in this cloud droplet. And then, of course, around that cloud droplet, we've got water vapor. And those molecules are bouncing around as well. And this is our vapor phase. And sort of the key idea here is that the liquid phase is a more constrained phase. And so these molecules in the liquid are actually going to be bouncing around a little bit slower, quite a bit slower than the gas phase. So these guys over here are bouncing around, but they're bouncing around slower. And then over here in the vapor phase, it's a much freer phase, and the molecules are bouncing around much faster. So as a result, you can think of the molecules in the liquid phase as being in a lower energy state. This is sort of a lower energy configuration, whereas the vapor phase is going to be a higher energy configuration as those molecules bounce around faster. Now let's suppose that we have some process that causes the liquid, so some of the molecules in the liquid phase are going to go into the vapor phase, which of course is evaporation, right? Liquid to vapor. So we've got evaporation occurring. So in order for this to happen, we're going to have to take some of these molecules down here, or well, over here in the liquid phase, that were bouncing around sort of in a lower energy state. And we're going to have to bump them up to a higher energy state so that they can become vapor, because the vapor molecules are bouncing around faster. And the only way we can do that is if we add energy to our system. And the way we're going to add energy to our system is by extracting some heat from the environment. So in the end then, in order to have evaporation occur, we have to extract some heat from our environment to add some energy to these molecules so they can bump themselves up to the higher energy state and become vapor. The end result then is that by extracting this energy from the environment, we end up cooling the environment. So evaporation is going to end up being a cooling process for the surrounding air. This, of course, is why it's always typically cooler after it rains, because as the rain falls and when it's on the ground as well, the whole time we're going to have that water evaporating. Some of that water is going to evaporate into the air. And in order to evaporate, it has to extract some energy from the environment to cause the molecules to bump up to the vapor phase. And by extracting that energy from the environment, it makes the environment cooler. Of course, we can go the other way. So we can go the other way as well. So again, we've got our vapor and we've got our liquid. But this time, we're going to take some of the vapor and we're going to transfer it into the liquid phase. So this, of course, is condensation, taking some of the vapor and transferring it into the liquid. Now, in this case, we have some of these molecules over here that were bouncing around in sort of their high energy state as part of the gas, and they're going to actually have to go into this lower energy state and become liquid. In order for that to happen, we're going to have to take some of that excess energy that these molecules had and get rid of it so that it can stick into this lower energy configuration. And what happens to that energy is ends up getting dumped to the environment in the form of heat. So we went from the higher energy state to the lower energy state, which means we had to dump the excess energy into the environment as heat. So as a result, condensation is going to be a warming process. It's going to be a warming process for the surrounding air. So that's basically how it works. And this is going to hold true, regardless of the kind of phase change you're looking at. If anytime you're going from sort of a lower energy, more constrained state to a higher energy, less constrained state, you're going to have to extract heat from the environment to do that, so it's going to be cooling. If you go the other way, from your higher energy, less constrained, to lower energy, more constrained, you're going to have to dump some of the excess energy, which means you're going to end up being warming of the environment. So with that in mind, it's probably worth going through a little table here where we list all the different ways we can transform the phase of water. And so we've got 3 columns here. The first one is describing the phase transformation, say vapor to liquid, et cetera, et cetera. The middle column is going to give the name, what we call that phase transformation. And then the last column, we're going to list whether that phase transformation is going to end up warming the surrounding air or end up cooling the surrounding air. Okay, start out with vapor to liquid. Vapor going into liquid phase was our condensation. Condensation. If we now have liquid going into solid, that's going to be freezing. Now, both of those should be relatively intuitive, But you can actually have a process that sort of skips the middleman as well. Instead of going vapor to liquid and then liquid to solid, you can actually skip the middleman and skip the liquid phase and go directly from the vapor phase into the solid phase. That happens all the time in the atmosphere. When you have ice crystals surrounded by water vapor, you can have some of that water vapor go directly to the solid phase on that ice crystal. And that process is referred to as deposition. Deposition. Okay, going to the bottom part here. If we have solid going to liquid, obviously that's melting. If we have liquid going to vapor, that's going to be evaporation. And then finally, just like on the first part, you can actually skip the middleman. Instead of going solid to liquid and then liquid to vapor, you can actually have solid going directly to vapor. Again, this can happen when you have ice crystals surrounded by vapor. You can have some of the ice crystal going directly into the vapor phase. And that's referred to as sublimation. Sublimation. Okay, what about the effects of these phase changes on the surroundings? Well, if you look at the top half of the table here, in the top half of the table, these are all phase changes that are going to be going from less constrained, higher energy states, like vapor, to more constrained, lower energy states, like liquid. Same thing with the second one. We've got liquid, and that goes to solid. Well, solid is even lower energy, so we went from the higher energy state of liquid into the lower energy state of solid. And of course, going from vapor to solid is going to be the same thing, going from the higher energy state to the lower energy state. And anytime that happens, we're going to have to take some of that excess energy that we initially had and dump it into the surroundings, which means that all of these guys are going to be warming processes for the surroundings. These are all going to be warming for the surroundings. They're all dumping energy. By contrast, here on the bottom part of the table, we're doing the opposite. For each one of these, we're going from a lower energy, more constrained state, like solid, to a higher energy, less constrained state, like liquid. And similarly, going from liquid to vapor, right? We're going from the lower energy state to the higher energy state. And then finally solid, which is our lowest energy state, going up to vapor, which is a higher energy state. So in all these cases, to go from the lower energy state to the higher energy state, we're going to have to extract energy from the environment, which means we're going to extract heat, which means we're going to end up cooling the environment. So these are all cooling processes. Now, sort of the main thing to keep in mind then from all of this is that when we have water vapor in the atmosphere, that water vapor is actually sort of a hidden form of energy, a hidden form of heat, if you like. Because, if we add water vapor to the atmosphere, that's not initially going to show up as heat, but sometime later, when that water vapor condenses into droplets, particularly in clouds, then that condensation process, going to the lower energy state, is going to end up dumping heat into the surroundings, and so you're going to end up warming the surrounding air that way. And so that happens through condensation. That also happens through freezing. Both of those are going to end up warming the surrounding air in your cloud. And as it turns out, this is actually a big mechanism. It's actually a bigger heat transfer mechanism than conduction and convection were. This transfer of energy through latent heat is going to be one of the big drivers, actually, of the circulation. Particularly in the tropics, where you've got all of these clouds forming and it's very moist down there. Every time those clouds form and condensation occurs, it releases latent heat into the environment, which makes it warmer. And it turns out that that warming associated with the latent heat is one of the big drivers of the global atmospheric circulation. Okay, so now a question. So we know from the previous screencast that the atmosphere doesn't really absorb that much of the incoming solar radiation from the sun. It does absorb some. You've got absorption in the ozone layer and in the thermosphere, and you've got some absorption of the visible as well. It wasn't zero. But for the most part, the incoming visible radiation from the sun passes straight through without being absorbed. So the question is this. If the atmosphere isn't getting its energy directly from the sun, then where does it get its energy? Where does the energy to drive atmospheric circulations come from? Well, the answer is going to be that instead of getting the energy directly from the sun, it's actually going to get most of its energy from the earth below. Right? It's still indirectly getting its energy from the sun because the sun is warming up the earth. But then what happens is that as the earth warms up, some of that energy that the earth absorbed from the sun is going to be transferred upwards into the atmosphere. Okay, so how does this happen? We usually refer to this as warming the atmosphere from below. We say that the atmosphere is generally warmed from below. So let's go through this process step by step. So the first step, of course, is that we've got this energy coming in from the sun in the form of radiation. So the first step is radiation from the sun, the bulk of which passes straight through the atmosphere and gets absorbed by the ground. So that's step one. Now, as a result, the ground starts to warm up. So step two is as the ground warms up, then the air immediately in contact with the ground starts to warm up as well. And this is happening through direct contact, through the motion of the individual molecules bouncing around, being in contact with the warmer ground, and then little by little transferring that heat upwards into the atmosphere. But if you remember, the atmosphere is not very good at doing that. So this is conduction, right? We're warming by direct contact and the molecules moving around. But the atmosphere is pretty poor at conducting heat that way. So it turns out that it's really a pretty thin layer that gets warmed through direct contact with the ground. It's surprisingly thin. It's on the order of centimeters or so that gets warmed directly by contact with the ground. But it does happen. You do get this layer of warm air down near the ground. The other thing that happens is that as the ground warms up, then it's going to end up evaporating some water vapor into the air as well. And if so based on what we just said, when we add water vapor to the air, that's a hidden source of heat because eventually down the road, when that water vapor condenses, we're going to end up getting heat out of it. So by moistening the atmosphere through evaporation, we have a hidden source of heat. Okay, so we've got this layer of air down near the ground that's warmed up and also moistened. Now what happens? Well, typically there's going to be some places that are warmed up a little bit more than others, and that air being warmer is going to be less dense, and so it's going to want to start rising. So some of that air that was warmed up by contact with the ground is going to start to bubble upwards. And typically these bubbles will start to coalesce into bigger bubbles, and you end up getting these thermals that are coming up off of the ground. So of course this is transfer of thermal energy by moving a whole air mass around, and that's always going to be referred to as convection if it's in the vertical, convection. So we have transfer of energy upwards by convection of the air mass. And then finally, our last step, if that air rises enough, and if it's moist enough, you'll actually form clouds out of it. We haven't talked much about this, and I'm not going to really explain it right now. We're going to explain it later in the course. But for the moment, you can just sort of keep in the back of your head that anytime you've got warmer air that's rising, if it's moist enough also, that's a good situation to produce clouds. That's typically how clouds are produced. If it's moist enough and it rises high enough, you'll end up producing clouds out of it. And if you do form a cloud, then that means that you're going to have water vapor condensing into droplets, which means you're going to end up dumping latent heat into the surroundings. That's what all these little arrows are around the cloud. That's the latent heat being dumped into the surroundings. So we've got our latent heat being added to the surroundings. Okay, let's go through that process one more time here. Bunk. Let's actually do this. Boom, boom, boom. So initially, the first step is we've got our radiation coming in from the sun, passing through and warming the ground. Step 2, the ground warms up, and it ends up warming a thin layer of air down near the ground through direct contact, i.e. through conduction. Because the air is pretty poor at conducting heat, it's a very thin layer, but it does happen. You also end up evaporating some water vapor into the air, which is sort of a hidden form of heat. Step 3, some of that warmer air down near the ground ends up rising in bubbles. And so that's convection, taking that warm air and moving it upwards. If you get that warm air rising high enough, and if it has enough water vapor in it, then you'll end up forming a cloud. And as the water condenses into cloud droplets, it releases latent heat to the surroundings. So all of these guys together then are ways of taking the energy that was initially absorbed by the ground coming in from the sun and transferring it upwards into the atmosphere. So we're going to end up warming our atmosphere from below. Now, on top of all that, we shouldn't forget about radiation. So we still do have radiation going on. If you remember, the Earth emits infrared, and a lot of that infrared gets absorbed by the atmosphere on the way out, which is another way of warming up the atmosphere as well. So we can't forget about that. So we've got all these things going on at once. We've got our conduction, convection, latent heat, and we've got radiation being absorbed on the way out. All are ways to transfer energy from the Earth's surface into the atmosphere. Here's a schematic that shows all of these sort of at once. You've got your radiation from the sun coming in and warming the ground. We've got a spot over here that warmed up a little bit more, and so it warms the air above it by conduction. That air being warmer wants to rise, that's convection. If it rises high enough and has enough water vapor, you end up getting clouds, which is going to release latent heat to the environment. And then finally, you've got your infrared radiation being emitted by the Earth and getting absorbed on the way out. All of these are transferring energy upwards into the atmosphere. Okay, now let's just take a minute or two to go through and talk about sort of a budget, putting numbers on all of these things. Now, it gets kind of complicated, as we'll see here on the last slide. So I'm not going to, sort of dwell on the individual numbers too much for this. But it's, basically as long as you guys understand the different processes involved, that's really mostly what I'm after. But that said, I do want to go through and at least introduce sort of, what this looks like when we put numbers on the different processes. Okay, so first, let's start with the energy that's coming in from the sun. So let's just say, to keep it simple, we've got 100 units of energy coming in from the sun. That energy passes through the atmosphere, and some of it ends up being scattered by the atmosphere back off into space. and some of it ends up being reflected and scattered off of clouds, back off into space. And some of it ends up reflecting off of the ground, again, back off to space. So if you put all this together, that's about 30%. About 30% of what was coming in just gets scattered and reflected back off to space. And if you remember, this has a name. This is called the Earth's albedo. This is energy that never enters the Earth system, right? It ends up just being sent back out to space. It's never absorbed, and so it's just energy that's kind of lost from the system. Now, of the other 70%, we've got a bit that's absorbed here. It's about 20% of the total that gets absorbed on the way through. Some of that is the thermosphere absorbing energy, some of that's the ozone layer, and some of that is the visible energy getting absorbed as well. The absorption of visible wasn't zero, it just was small. So it ends up about 20% of the energy is absorbed directly by the atmosphere. So what's left? We've got 30% being scattered and reflected away. We've got 20% being absorbed. So that means about half makes it through to the ground. So about half of the incoming energy gets absorbed by the Earth's surface. So what happens next then is that this energy that's absorbed by the Earth's surface, a lot of it ends up getting transferred upwards into the atmosphere. And this is where all those processes that we were just talking about come into play. And it gets kind of complicated. You can see from this figure that, the total budget here is actually sort of a complicated combination of all of these processes. And I'm not going to expect you guys to remember the numbers on this diagram, just as long as you sort of know, what the processes are. Maybe have a feel for which ones are bigger and which ones are smaller. That would be good too. So we've got our 50% that comes in and gets absorbed by the ground, and then it starts to get transferred upwards. That happens through conduction and convection, transferring energy upwards. We've also got our latent heat, right, as we've got water vapor added and then condensing in clouds. You'll notice that the transfer of energy through latent heat is actually a much bigger number than the direct heat transfer through conduction and convection. It's almost 3 times as big. And then you've got your radiation, which is an even bigger player. So you've got all of your infrared radiation off of the ground, and a lot of that gets absorbed by the atmosphere on the way out. Some of it gets through, but actually a big chunk of it, probably the bulk of it, gets absorbed on the way out. And of course, transferring energy to the atmosphere means the atmosphere warms up, and then the atmosphere starts to radiate away its energy as well because it's warming up, and it radiates part of it upwards and part of it downwards here as well. And the part that comes downwards is, again, the greenhouse effect, right? We're getting some of that energy that was lost to space, that would have been lost to space, is now being absorbed by the atmosphere and then re-radiated back to the Earth, and sort of energy that gets recycled back downwards and keeps things warmer than it would have been otherwise. Okay, so that's the whole thing. This is sort of the end of our discussion of basic ways that energy gets transferred through the atmosphere system. So with the next screencast, we're going to shift gears just a little bit. We're still going to be talking about energy, but sort of more of the implications of this, particularly with what it means with respect to how the seasons work.